will now look at the most important organ of our body, that is human eye. And without the human eye there is no life, and it is supposed to be the important organ of the human body, and that's the reason we can define the human eye as the most significant. It's most significant because it enables us to see the beautiful and colorful world around us. So it is just like a camera. So how the pictures are captured in a camera, so whatever the things you are observing are captured in your human eye. So it consists of various parts. Outer portion of the eye we are very familiar, and you can think of eyeballs, iris, all these things are the terms known. But behind the scene, behind the eyeball, you have some other parts. And how does this exactly works? How does the eye function? That is what we are to learn. So the various parts of the human eye and their functions are as follows. So one after the other we'll just look at. So whenever you think of a human eye, so during the Diwali and all, most of the people gets affected with the cornea. So cornea is the outer layer where the light enters into the eye through a thin membrane. It's a thin membrane, thin layer, that is called as cornea. The first affected thing is cornea. Cornea can be replaceable in fact. So it is on the front surface of the eyeball. So whatever is visible to you, so just above the eyeball, front side of the eyeball, you can see the cornea. So obviously you can look at the curvature of the eye, you can see it is spherical in shape. So it's spherical in shape, cornea is spherical in shape. You can just look into the figure how the cornea is placed, and it refracts the light. That means whenever the light falls onto the eye, it undergoes a refraction, and from the outer surface whatever the light falls, majority of the portion will get refracted. Then comes the pupil. Pupil is one which controls and regulates the amount of light. That means lot of light is falling onto the eye, but only a portion will be taken. That means depending upon the intensities and all, the pupil controls the amount of light that enters into the eye. And this pupil, size of the pupil is controlled by iris, and no two human beings will have the similar iris. That is the reason in Aadhaar cards and all we are using this iris mechanism. So it is a dark muscular diaphragm that controls the size of the pupil. So when the size of the pupil is controlled, obviously the amount of light enters also will get controlled. And you can see in the image, most of the portion of this human eye is mentioned as a blue in color, and two types of liquids I have mentioned. One is aqueous fluid, the other one is vitreous fluid. So these fluids, generally you can see the eye, whenever you look at the eye, it is watery somewhat. So that is the reason whenever you think of the fluids before the diaphragm, the pupil, that is called as the aqueous fluid, and behind that it is vitreous. So that is how the liquids are mentioned over here in the figure. Then comes, after entering through the pupil, cornea is the first portion, then enters through the pupil, iris controls the size of the pupil, and behind this diaphragm you have a crystalline lens which is controlled by ciliary muscles. You can see the ciliary muscles in the diagram, which will move here and there so as to adjust the focal length of the crystalline lens. Crystalline lens is just like the lens system of our camera. So this crystalline lens will get the image of whatever the object you are looking at, and it provides the finer adjustment of the focal length required to focus the objects. Whatever you have seen, a distant object or nearer object, whatever it is, that focus can be on the retina with the help of a adjustment of the focal length of crystalline lens. And ciliary muscles make the crystalline lens to move freely so as to make the adjustment. Ciliary muscles are, as shown in the figure, just surrounded to the crystalline lenses. Now the next comes is retina. This is the crucial part. This is an important part of our human eye. Retina cannot be replaced. So here focus from the lens falls on the retina, which is inverted of course, and it will give, then again your brain can interpret to so as to get the real image of course. So focus from the lens falls on the retina, that is inverted, and it has got sensitive cells, because here all the information gets recorded, and these cells are made of cones and rods, because you are looking at the colorful world which is having the number of colors, because light is made of different colors, so you are observing the different colors with your eye. So cones sensitive to bright light and rods are sensitive to dim light, because all the portions whatever you observe may not have the same intensities. You are observing the bright things as well as the dark things. So bright light is observed, that means the reciprocation is due to the cones, and here dim light is due to the rods, and the colors are sensed by cones. So cone sense the color. So that is how retina consists of the cells, sensitive, light sensitive cells. And here once this information is collected, it senses the colors and the sizes, all those things, then it will send it to the optic nerve. Then it will be, these cells generate the electric signals and send to the optic nerve. The next thing is optic nerve. So optic nerve function is, it carries these signals to the brain. So whatever the information provided by the retina to the optic nerve is carried to the brain, where brain interprets that information. So here, as I explained, the crystalline lens, the focal length and the movement of crystalline lens is just because of the motion of the ciliary muscles, and in fact it is some watery content, so there will be a sufficient lubrication so that you can move your eyeball such that because of that the lens easily with the help of this lubrication. So this optic nerve gives the information to the brain, and brain is an organ which interprets the information and gives the sense of vision to us. That is how the function of human eye. And here one more point you need to remember, at the junction of optic nerve and retina, there is no presence of sensory cells. So the sensory cells, what I said here, they are present in the retina, but at the junction where the retina meets with the optic nerve, there are no such sensory cells. So definitely when there are no sensory cells, there won't be any vision over there. So that is what called as the blind spots. People are blind because of the focus is falling onto this blind spot. That's the reason they are able to look at the things. So the junction of optic nerve and retina, where you don't have any sensory cells, that point is called as blind spot. So this is one definition you need to remember. But overall, about each term associated with the human eye, so by looking at the figure given, you can see the various parts, how they are accommodated, how light is entering and how it gets controlled and how it is sensed, then how it is transferred to the brain. All these things you can easily explain with the help of functionality of each and every terms associated with the human eye. So these are the things you need to remember, and this is an important thing to as far as examination point of view, as well as in our day-to-day activity, you need to know about the terms associated with the human eye. We'll now look at a chapter called Human Eye and Colorful World. Here, first we'll see the human eyes. Human eye is nothing but made of natural lens in fact, and it consists of the various parts which we have already seen in our previous video, and we'll just recap the things what we have seen, then discuss about how the human eye focuses anything that we see, that means an object, how it is focused into the human eye. So as far as the parts are concerned, so looking at the image, you can think of first you have cornea. Cornea is one which allows the light to enter into the eye. The second one you have pupil. Pupil makes how much amount, it controls, in fact controls the amount of light to get entered, and the size of the pupil is controlled by an iris. So all these things we have already seen. Iris is a dark muscular diaphragm that controls the size of the pupil, and then you have backside of this pupil you have ciliary muscles. So these ciliary muscles will move, contract and expand so that the lens, eye lens can be either contracted or expanded. That means its focal length can be varied. So after this eye lens you have retina. Retina is one which takes the information and sends it to the optic nerves, and optic nerve is one which carries the electrical signal to the brain, that is optic nerve. All these things we have already looked into this optic nerve. And the two other things what exclusively we are to look at in here is aqueous humor, which forms before your cornea and the crystalline lens. It is a fluid, a watery type of content. Actually, it balances the pressures as well as provides the nutrition for central cornea and lens, because they don't have their own blood to carry it as a nutrition. That is the reason the aqueous humor helps up to be a nutrient supplement for this cornea and crystalline lens. That is the aqueous humor. Then you have vitreous humor. Vitreous humor is one which is behind the crystalline lens, and it is also a jelly type of content where it forms as a lubrication for ciliary muscles and all, so that the entire all the parts are inside this vitreous humor backside of this lens. And these are the two humors in addition to the parts we have already discussed. You have to remember these two, and these are nothing but a jelly type of thing, a watery content parts in the eye. And now, in order to focus onto the object which is at a distance, if the object is at distance, then these ciliary muscles expand. So focal length increases, but converging power is less. So ciliary muscles will make the eye lens to either increase the focal length or decrease the focal length depending upon the object. Object is at a distance. That means to focus the distant object, ciliary muscles expand. So focal length of the eye lens increases and it becomes thin. And the other case is object is at near point. Object is at near point. In that case, when object is at near point, in this case what happens? Ciliary muscles contract, and in this case focal length decreases, and here converging power is more and eye lens become, in this case eye lens becomes thick in this case. So this is how there are so many things that you can remember in this, and you have cones and rods, and cones identifies the colors. So rods can look into intensity of light. It detects, the rods help to detect the intensity of light, and cones help to identify the color. So these are the several things that you need to remember in case of the human eye. So human eye, the diagram is very important. So you have to draw the diagram, then explain each and every part. So each and every part has got their own functionalities, and in detail we have already discussed in the previous video, and now just for the recap we are just writing all these things and try to get these two things were not covered in the previous video. That is the reason specifically we are discussing about the aqueous humor and vitreous humor. Aqueous humor lies between the cornea and the eye lens, whereas vitreous humor is backside of the eye lens, the all watery content, a jelly type of content. And in this jelly type of content, these muscles can contract and expand, and based upon this contraction and expansion, yeah, the focal length of eye lens is managed. That means the focal length increases if the object is at distance, decreases when object is nearby, and how the converging power will vary, and how the focal lengths vary. All these things we are to look at in due course of time. Now we look at one phenomenon of light, that is called dispersion. So far we have seen the reflection, refraction, radiation, so many things. Light is in the form of radiation. It does not require any medium, I said. So it's a radiant energy in fact. And we have seen reflection, how a light ray falls on the mirror, reflects back, or any other surface reflects back, and how it refracts everything. Now we are going to look at what does it mean by dispersion. Dispersion is nothing but splitting up of light into its constituent colors. Splitting up of light into its constituent colors is called as dispersion. That means generally light is white in color. So that's the reason we call it as white light. So whenever a white light is falling onto a prism, here this is the instrument which we are going to look at in detail now. So what is a prism and all we'll be discussing. So if at all you have a prism, and when a white light is falling on that, so with reference to the normal, this is the white light. So the white light is falling on that. When white light falls on the one of the surfaces of the prism, then it will get dispersed. It will get dispersed into its constituent colors. It will get dispersed into its constituent colors. That means you have the 7 colors. So when it comes out in the form of 7 constituent colors, and violet bends more compared to the red. So from violet to red, you are getting 7 colors called Vibgyor. So this is a pattern what you obtain: violet, indigo, blue, green, yellow, orange, red. So a white light when falls on the prism will get converted into its constituent colors, that is 7 colors, and this phenomenon is called as dispersion. So in simple you can define dispersion is the phenomenon of splitting up of light into its constituent colors. Now how it is getting dispersed, and what the prism is doing over here, and what is the purpose of considering the prism, and what are the properties of prism, all these things we have to look at. And here when you think about the prism is an instrument where a light can get dispersed. That is the first point you need to remember. And using this prism you can even calculate the refractive index of the material of the prism. That is the second point you need to remember about the prism. That means we are able to calculate the refractive index of the material. If prism is made of glass, then the refractive index of the glass. Prism is made of water, then refractive index of the water, and whatever the material this prism has, you can find out the refractive index. So this is one of the ways of finding out the refractive index. So earlier we have seen the refractive index formulae as velocity of light in vacuum divided by the velocity of light in medium gives rise to the refractive index. The other formula is due to the Snell's law, and this is one more formula where you can find out the refractive index. First of all, let us learn what is prism and what is its structure, and the concerned parameters, what parameters we are to look into this prism, design of a prism. Actually it's a 3-dimensional aspect. So in detail when I look at the prism, so prism is a 3-dimensional picture. So it appears to be like this. So the actual shape of the prism is going to be like this, and here it has got 3 rectangular surfaces, A, B, C, A dash, B dash, C dash, let us say. So it has got, this is one rectangular surface, this is second rectangular surface, this is third rectangular surface, and two triangular surfaces. So one is ABC, this is one triangular surface, and A dash, B dash, C dash is the second triangular surface. So it's a three-dimensional picture of the prism, and the portion which rests on the ground is called as the base. So this is going to be the base of the prism is this. So this is called as the base, and this is called as refracting surface. So it has got two refracting surfaces. This is one more refracting surface, two refracting surfaces, and one base. So here it is made of, so in particular you can write, it has three rectangular surfaces, and here you can denote it as B dash, C dash C, and AB, B dash, A dash. This is one more surface, and the other surface is A dash, C dash, C. So these are the surfaces. In fact, you can call it as B dash, C dash, C, and again coming back to B. This is one surface, and here AB, B dash, A dash, and again back to A. So this is one surface, and the third surface is going to be A dash, C dash, C, and again back to A. These are the three rectangular surfaces and two triangular surfaces. And that is ABC is one thing, A dash, B dash, C dash is one thing. So when you look at this in a cross-sectional way, the cross-sectional view of the prism is going to be like this. So when you are looking at a side view, the side view is going to be like this, and this is what we call as A, B, C, whereas BC is resting on the ground. That is the reason you call it as BC. And now this is called as base. So this is the base, as I have mentioned over here. Opposite to the base, whatever the angle you have, this angle is called as angle of prism. This is the angle which is called as angle of prism, and you can also call it as refracting angle. So if it is an equilateral triangle, the prism is of equilateral triangle shape, A is treated to be, A is generally 60 degrees. So for equilateral prism. So this is the thing you need to consider when you are looking into the prism parameters. So using this prism, how to calculate the refractive index, all we will be looking at. So here the summary of this entire lecture is that dispersion is the phenomenon where you are splitting up of white light into constituent colors, and that can be observed with the help of a prism. So when white light falls on one of the refracting surfaces from the other refracting surface, you are getting the dispersed light, and the structure of the prism is going to be like this. It's a three-dimensional view, and coming to the two-dimensional view, it appears to be same, and overall it has three rectangular surfaces and two triangular surfaces, and a cross-sectional view of the prism is going to be like this, and various terms associated with the prism are to be in this manner. So this is how the prism can be described, and using the prism, how to calculate the refractive index, all we are to look into now. Now we look at the refractive index of the material of a given prism. So generally, refractive index means it is nothing but the refractive index is one which identifies the nature of the material, of course, because as a standard phenomenon we have seen glass. Refractive index of glass is going to be 1.5 and refractive index of water is going to be 1.33. Refractive index of air is going to be 1. So likewise, it designates the denser, whether it's a denser medium or rarer medium, whether it's optically denser or optically rarer, something like you can identify the optical nature with the help of the refractive index. That is the reason it is always convenient for us to find out the refractive index of a given material. That's the reason we are finding out the refractive index with the various sources. One of the sources is by using the prism. So whatever the material is given, that you are taking in the form of a prism, and using that prism we can calculate the refractive index as follows. So here let us suppose this is the prism given to us. This is the prism given to us, and here we are to look at, so an equilateral prism I am considering, and using this equilateral prism we are calculating, we are finding out the refractive index of that. So here let us suppose this is the equilateral prism I have, and now this is the normal drawn to the prism, and here a ray is incident, then refracted back. So let us say this is the incident ray, this is the emergent ray, and this is also always measured with reference to the normal only. So let us say this is normal 1, this is normal 2, and of course this is the prism angle A. So here, as per, if I continue this, extend this, this is continued somewhere like this. So we can just think of, so this is the prism. So when I extend this, the picture is going to be like this. So this is the ray, how it is getting refracted. So, and this is going to be the base. Now let us say this is the incidence angle I1, this is the refracted angle at first surface. So these two are the refracted angles A, B, C, let us suppose, and this is the refraction angle 2, and emergent angle, let us say this is I2. I2 is the emergent angle. Now looking at these parameters, we need to calculate what is refractive index of this prism. So first of all, I'll just consider some, I call this as M. So considering the triangle, let us say this is P, this is P, Q, R, S. So PQRS is the path of the ray that is following. Now consider the triangle AQR. Angle A plus angle Q plus angle R. Angle A plus angle Q plus angle R must be equal to 180 degrees. Here angle A plus angle Q can be written as, since it is a normal, it will become 90 minus R1. 90 minus R1 plus angle R is going to be here 90 minus R2, that is going to be 180 degrees. Therefore simplifying this I can get A is equal to R1 plus R2. Let us say this is equation 1. Now looking at the second case, see here, if at all this ray is not undergoing the refraction, it would have gone in undeviated path like this. So the original emergence is this. This is the original emergence. That means it is deviated by this much. So when it is deviated by this much, then deviation angle can be written as, this deviation angle can be taken as exterior angle is equal to sum of the interior angles. Exterior angle is equal to sum of the interior angles means, so D is going to be I1 minus R1, this angle, interior angle. So D can be calculated as exterior angle is equal to sum of the interior angles. Therefore, angle D is going to be I1 minus R1 plus I2 minus R2. That comes out to be I1 plus I2 minus R1 plus R2. So this is the deviation angle. Let us say this is equation 2. If at all the incidence angle is changing, then deviation angle also changes. Initially, as I is increasing, D will decrease. If you draw the graph between I and D, ID graph nature comes out to be like this. You are taking I over here, deviation angle over here. So it will gradually decrease first and then increases. So the angle at which it takes the minimum value is called as angle of minimum deviation. So DM is called as angle of minimum deviation. And at this place, at the angle of minimum deviation, I1 will become I2 and R1 will become R2. This is the condition where I1 and I2, that is angle of incidence, angle of emergence become same, and angle of refraction at the first surface will become equal to angle of refraction at the second surface. Therefore, substituting these values in 1 and 2, substituting these values in 1 and 2, equations 1 and 2, so I will be getting A is equal to 2R, which implies R is equal to A by 2, and this angle is going to be now minimum deviation angle. Therefore, DM comes out to be 2I minus 2R, which is nothing but 2R is nothing but A. Therefore, I comes out to be A plus dm by 2. So R value and I value we have got. Now you can use Snell's law. Using Snell's law, we can get mu is equal to sin I by sin R. So I is equal to A plus D by 2, A plus D by 2, and R is equal to A by 2. So substituting the values, I will be getting mu value as sin of A plus dm by 2 divided by sin of A by 2. So this is the final expression to find out the refractive index of a given material. So this is how the derivation will occur. But as far as our curriculum is concerned, we need to remember only the formula, that is mu is equal to sin A plus D by 2. Derivation of, this is what we have done, mu is equal to sin of A plus D by 2 by sin A by 2. This is a thing you need to remember for solving the problems. So this is what about the derivation for the refractive index of a given material using the prism. We have seen the various functions of the eye and various parts and the pictorial representation of human eye in the previous videos, and one of the parts of the human eye are the ciliary muscles. So here ciliary muscles will make the human eye, that is eye lens in fact, to change its focal length, because when ciliary muscles are relaxed, the focal length is increased. Therefore, the eye lens becomes thin. Eye lens becomes thin in the sense focal length is increased so that it can see the distant object clearly. Similarly, when ciliary muscles are contracted, eye lens becomes thick. Therefore, focal length decreases. Therefore, it can see the nearby objects clearly. That means ciliary muscles are responsible for changing the focal length of the eye lines by properly adjusting the eye lens, either making it thin or thick. So when it makes thin, when it becomes thin, that is by means of relaxation of ciliary muscles. When ciliary muscles are relaxed, then eye lens becomes thin, then focal length increases so that distant object can be easily seen. And now that means ciliary muscles are making the curvature of the eye lens to get adjusted accordingly depending upon where the eye is focusing. So these are the two cases where you can see the nearby objects or distant objects with the help of the eye lens modification. Now the ability of this eye lens to get adjusted with its focal length, that means to look at the distant object the focal length has to be increased, and to look at the nearby objects the focal length has to be decreased. Such ability of adjusting itself depending upon where the eye has to be focused, there will be a power of accommodation. That ability of eye lens to get adjusted is called as power of accommodation. And now eye lens can see the objects clearly when they are kept at a distance of 25 centimeters from the eye. That means for normal vision, if at all anything is kept near the eye at a 25 centimeters, it can see it clearly. Such a distance is called as least distance of distinct vision. Here you can define the least distance of distinct vision as the minimum distance of an object from the eye where the eye can see the objects clearly. That means without strain, you can see the objects clearly if at all they are kept at a distance of 25 centimeters, and that 25 centimeters is called as least distance of distinct vision. Now we are going to look at how the defects arise for human eye. That means if human eye is not in a position to look at the objects clearly, then you say that there is some defect in the eye. And how do these errors come in, these defects come in for the eye means because of the reason if the focal length of the eye lens is not properly accommodated, that means power of accommodation is not proper. If an eye loses the power of accommodation, then it leads to the defect in the vision. That's the reason the vision is going to be blur and you cannot see the objects properly. So if at all you are not able to see the objects properly, depending upon the position of the objects, there can be three different types of defects arise. One of them is, the first one is called myopia. And this myopia is often called as short-sightedness, which means the eye with this defect can see the nearby objects clearly and which cannot see the farther objects clearly, because the far point of this defected eye is not far away but towards the eye, as shown in the figure. So you can just look into the figure over there. You can check the far point is not at infinity, it is somewhat nearer. In that case, here the image is formed in front of the retina. That you can observe in the figure shown here. So the image is not formed on the retina, it is somewhat before the retina it is formed. That is the reason he can see the nearby objects clearly but not the farther objects, because farther objects the focus will be before the retina itself. That is the reason farther objects cannot be seen properly. In such case, this defect can be corrected with the help of concave mirror, concave lens, in fact, not the mirror, concave lens. So by keeping the concave lens before the eyeball, before the eye lens, the image which is formed before the retina can be got back to the retina so that the correction can be done. That means in order to recover, in order to overcome this myopic defect, we have to use a lens called concave lens. Concave lens is used to rectify the defect called myopia. So the various points you need to remember in this is, myopia is also called as short-sightedness. That means the eye can see the nearby objects clearly but not the distant objects. And here in this case, far point of this defected eye is not far away. That means it is not at infinity. Not far away means not, that is not at infinity, but towards the eye, it is somewhat towards the eye, and image formed is in front of the retina, not on the retina. So in order to get back the image onto the retina, we have to use a concave lens, and all these points can be easily depicted with the help of the figure given over here. We will now look at the second type of defect of an eye, that is hypermetropia. So here hypermetropia, here look at the figure, and as per the figure you can see that the image is formed beyond the retina, meaning that generally whenever the image is formed on the retina, that can be seen clearly, but here in this case it is a long-sightedness defect. That means only the objects at long distances can be seen clearly, distant objects can be seen clearly, that is what, and image is formed beyond the retina, and this defect can be corrected with the help of a convex lens of suitable power placed before the eye lens. That means actually what is happening, the image is not formed on the retina, in fact it is formed beyond the retina. The reason for that is, the near point for this defect is not exactly at the 25 centimeters, but near point is away from the 25 centimeters. That's the reason the focus is, the image is focused not on the retina, it is beyond the retina. It has to be brought back to the retina. For that sake, we are using a convex lens. A convex lens has to be placed before the eye lens so that the correction can be done. Now the image is formed on the retina so that the hypermetropic error can be corrected. So that is how you can correct the hypermetropia with the help of a convex lens. That means the key points you are to remember here is, the hypermetropia is a defect called as long-sightedness. That means only distant object can be seen clearly but not the nearby objects, and here the image formation is beyond the retina, and the defect can be corrected with the help of a convex lens. And the ray diagrams for that, here the near point is not at 25 centimeters, it is beyond 25 centimeters. So power of accommodation of the eye lens is not proper, it is not accommodating at 25 centimeters, it is accommodating at more than 25 centimeters. So a correction is required, and that correction can be done with the help of a convex lens. So you can look at how hypermetropic eye has a defect and how it can be corrected with the help of the figure shown. Now we look at the third type of defect, that is called presbyopia. Here we have seen what is myopia, what is hypermetropia. Myopia is a defect by means of which only nearby objects can be seen clearly, and that can be corrected by means of the concave lens. And hypermetropia is the defect by means of which you can see only the distant objects, nearby objects cannot be seen, and that can be corrected with the help of the convex lens. So these are the things we have seen, and generally the defects arise due to the loss in power of accommodation of the eye, but it is not only because of the defects arising due to the variation in the focal length and all of eye lens, but also due to the age. Over the age, these ciliary muscles will get weakened. Because of the weakening of the ciliary muscles over the age, ciliary muscles gets weakened, hence they cannot see, adjust the eye lens properly due to the lack of flexibility, which leads to a defect called presbyopia. That means because of the weakening of the ciliary muscles and there is no proper flexibility of eye lens, that leads to a defect called presbyopia, by means of which it cannot see the nearby objects properly. That means it is one fact of hypermetropia, and sometimes over the age the old people will get both the defects, that is myopia as well as hypermetropia, and these defects are together called as presbyopia. That means the defect of eye due to the age is a combination, or sometimes only the myopia or only hypermetropia, or sometimes the combination, and this defect due to the age factor is called as presbyopia. In such case, people need to use the bifocal lenses. Bifocal lenses they need to use. Bifocal lens, such that the upper portion is concave and the lower portion has to be convex. That means if you have a lens like this, then it is a bifocal. That means this portion is going to be concave and this portion is going to be convex. Likewise, they have to use in order to rectify the presbyopia error. So, presbyopia defect is arising due to the age factor. And apart from this, if at all the crystalline lens is covered by somewhat a milky layer, then the vision becomes blur, and such milky layer is called as cataract. So this can be removed with the help of a surgery so that the vision can be rectified. So this is also coming due to the age factor. So these are the various defects that arise in the human eye. So all defects are due to the variation in the power of accommodation. That means if power of accommodation is lost, then that leads to the different types of eye defects. So these are the various eye defects and the rectification mechanism. So in broad, we are to look at three types of defects, that is myopia, hypermetropia and presbyopia. So these are the major defects generally we come across in case of the human eye. Now we look into some natural phenomena that we observe due to the sunlight. That is, when sunlight interacts with the several things around us, it gives rise to the beautiful phenomena, like you can see the color of the sky as blue. This is one of the natural phenomena due to the sunlight. And you can see the rainbow's formation. The rainbow is formed just after the rain in the presence of the sunlight. And you can see the atmospheric refraction, just like the Tyndall effect and all comes under atmospheric refraction, and the clouds are of different colors. That depends upon how the light is falling on that. White clouds, reddishness sun, and at the time of sunset and sunrise, the sun changes the color from white to red, orange, the different changes that occur. These are all the phenomena that occur due to the natural interaction of sunlight with the things around us. So one of the applications, one of the natural phenomena that we can look into here is the formation of rainbow. Here the rainbow is formed. It's a common experience for us that rainbow is formed just after the rain when sunlight comes up. So see here, in the atmosphere, when the raindrops are present, the sunlight, when falls on a raindrop, it undergoes a refraction as well as the dispersion. So here the rainbow formation is due to the two different phenomena. One is refraction, the other one is dispersion. See here, whenever the sunlight is falling on the surface, so this is a rarer medium, this is a denser medium. So raindrop, it's a water, it's a denser medium, so it undergoes a refraction, and simultaneously it also undergoes a dispersion. That is the reason the white light is getting split up into the vibror, 7 colors, violet is being deviated more, it bends more, whereas red less. That is the reason you are getting the color, the white light split up into 7 colors ranging from violet to red. Now further, it undergoes a reflection at the other surface because the medium from here to here it is same, so it undergoes a reflection. Then when it comes out of the raindrop, again it is coming back into the atmosphere, so that it will be dispersed at different angles. That's the reason you can see the violet and red separated as the 7 bands, which appears as a rainbow. So here you can see that the outer layer is going to be the red over here, being the inner layer as the violet. So this is how a rainbow is formed. That means the phenomena involved in the formation of rainbow is, here it is undergoing 2 refractions and 1 reflection. 2 refractions, 1 reflection here, and the dispersion. Dispersion is nothing but splitting up of white light into 7 constituent colors that we have seen with the help of the prism earlier. Here the same phenomenon is occurring because of the refraction, reflection and dispersion. The rainbow is formed. This is one of the natural phenomena of the sun. The other thing you can see is scattering of light. Why the sky appears blue means because of the reason scattering. That means whenever light falls on the atmospheric particles, depending upon the size of the atmospheric particles, it will be scattered. So most of the light scattered by the molecules of the atmosphere are, the blue light has got the shorter wavelength. The blue light has shorter wavelength, so that get scattered in greater directions, greater amounts. So whatever the light that is not much scattered can travel to the longer distances. So here most of the light is scattered is blue. That is the reason sky appears blue. Likewise, you have the various phenomena, one after the other we'll look into. So far we have seen how the rainbow is formed. So rainbow, formation of rainbow is due to the dispersion as well as the refraction, I said. So here we will look at the other natural phenomena of sunlight, that is scattering of light. So here whenever a light passes through the atmosphere consists of the molecules of various sizes. So whenever the light passes through these molecules absorb the light and then emit the radiations in all possible directions, and that phenomenon is called as the scattering. See here, if the molecules after absorbing all the radiations emit in all possible directions, that phenomenon is called as the scattering. That means emission of the light after absorption from the sunlight is called as scattering. Scattering is nothing but emission of the radiations falling on them by the molecules. See here, if at all the wavelengths, whatever the wavelength absorbed, because light is coming to the molecules and it has got certain wavelength, and whatever the wavelengths absorbed by them are equally emitted back, then you call it as the elastic scattering. That means if the wavelength remains unchanged during the scattering, then you call it as the elastic scattering. Now here, according to the Rayleigh criteria, a scientist called Rayleigh, according to him, so it totally depends upon the intensity of the scattering light, totally depends upon the wavelength. That means intensity of scattered light is inversely proportional to the lambda power 4. That means amount of the scattered light depends upon the nature of the molecules as well as the wavelength of the light. So here it is to be observed, blue light is scattered much more than the red light. That is the reason whenever the light passes through the atmosphere, most of the light scattered is blue. That's the reason the sky appears blue, because blue light is scattered more. So that is a point here to be noted. Blue light is scattered much more than the red light. And here you can also have one more explanation for why the sun appears red during the sunset or before the sunrise, why the sun appears red. So if you look into that, in the mid noon, during the midday, it appears whitish, whereas when it comes to the sunset time, it appears to be reddish. The reason is, when the sun is at the horizon, the light coming out of the sun has to travel through the atmosphere for the longer distances. So when the light travels through the atmospheric particles, most of the light that's scattered is blue. Therefore, blue color is scattered away. Only the remaining will be reaching to the human eye standing at the distant point. That is the reason the leftover light is only the red color. Hence, it appears to be red. That means when sun is farther at farther distance, the remaining colors are scattered off. Only the red color whose wavelength is high, the higher wavelength light will be reaching to the person, and that you can observe in the figure which I have given in this. And now one more point you need to remember, why the traffic signals, the danger light is red in color, means because it can be reached to the longer distances without any scattering. That means at longer distances also it can be seen clearly. That is how the traffic signals or danger signals are always in red color. That is one more point you need to remember here. So scattering of light, as a conclusively you can say, scattering of light is due to the absorption of radiations by the atmospheric molecules and emit the same. So the radiations that are coming emitted by the atmospheric particles after absorbing the sunlight is called as the scattering. So here 2 points you need to remember: the reddishness of the sun as well as the sky appears blue. That is because of the scattering nature of the light, and this is one of the applications of the natural phenomena of light. So rainbow is one application and scattering of light is the other application, and now we look at the other cases also. Now we have seen the different natural phenomena of sunlight, right from the rainbow, formation of rainbow, the scattering of light, and one of the features of the scattering of light, one of the applications of the scattering of light is Tyndall effect. So Tyndall effect is nothing but the phenomenon of scattering of light by colloidal particles such as water, dust particles in the atmosphere. See here, in this case, whenever the light passes through the colloidal particles, the radiations are absorbed and are scattered by the colloidal particles. Means generally it is composed of the mist. Mist consists of the watery content and dust particles. Such particles will scatter the light. So as an example, you can see such phenomenon in case of a closed room in which a small hole is made. When a sunlight is allowed to pass through this, then the radiations from the sunlight, the radiations of the sunlight are absorbed by the particles and are scattered, and they scatter the light. So here it is consisting of the particles as well as the light. Since the light is scattered, then particles becomes clearly visible. This is a practical phenomenon that you can see in a closed room where the light is allowed to through a fine hole. In that case, the particles are visible because of this Tyndall effect. That means the scattering of light takes place due to the colloidal particles. So this phenomenon is a Tyndall effect. The same phenomenon you can observe in dense forests also. So when the forests are too thick, very thick, then whenever the light enters into the fine gaps of that, the mist particles, so the tiny water drops in the mist scatter the light. So that means here what happens, whenever the light is absorbed by the water droplets over here will be scattered. That's the reason a fine canopy can be observed in a dense forest. That is also due to the Tyndall effect. So this is also one of the features of the scattering of light. Now another phenomena, the natural phenomena that occur due to the sunlight is atmospheric refraction. That means whenever the light passes through the Earth's atmosphere, it undergoes a refraction. As we know that refraction is due to the bending of light when it passes from one type of medium to the other type of media, that is rarer medium to denser medium or vice versa. So here whenever the light comes from the upper regions and enters into the atmosphere, the refractive index of the atmosphere changes. That's the reason obviously the path will get deviated. Hence you cannot see the real position of the star. That means, so as you are moving, as the conditions are changing, refractive index is changing, physical conditions are changing, due to which you cannot see the star every time with the same brightness and same intensity. Instead it will be flickering as the conditions are changing. Such type of refraction is due to the atmosphere, and we call it as the atmospheric refraction. Here in this case, an example we can see that whenever there is a flame, so near the flame, if at all you are observing, here is the flame, when you are observing any object over here, any object over here through this flame, you cannot see this object as stable. In fact, you can see this object as somewhat a wavery, that means in the shaky manner, because of the reason when you observe the air particles near the flame, these are hot enough so that less refractive index, whereas the refractive index above this is more. Because of the variation in these refractive indices, here there will be a deviation in the path. That means the light ray will be deviated, and since this flame is not unique every time, it is changing its refractive nature, this object will not be seen as an ideal one. In fact, it will be looking as a wavery thing. That's the reason wavering or flickering of objects when seen through the stream of hot air above the fire are because of the atmospheric refraction. That means this atmosphere will not have the same refractive index all the time, that vary depending upon the particles present, that vary depending upon the conditions prevailing at that particular instant of time. So such type of refractions, because of the changes in atmosphere, because of the change in the density of the atmospheric layers that occur, that is called as atmospheric refraction. And one more example you can think of, twinkling of stars. Twinkling of star is also the same thing. When you are observing a star, so you can just look into the figures provided over here. So when you look at the star, if at all the atmosphere conditions are not changing, and right from the star to the earth, if you have the same atmospheric conditions, then always the star seems to be at the same intensity and at the same brightness, same luminosity, everything. But when this atmosphere is changing, the intensity is changing, because the apparent position of the star will not be same, because it undergoes a bending through the atmospheric layers. Then the position is going to change. Because of the change in position, the brightness of the star will not be unique every time. That is the reason it gives a twinkling effect. So because every time the position, the apparent change in position occur, which gives rise to the different intensities. And similarly in case of sunrise and sunset also, before the sunrise, so 2 minutes before the sunrise, 2 minutes after the sunset, you are able to see the sun, because of the reason over the horizon the refraction takes place. Because of this refraction, you can see the sun before sunrise as well as after the sunset also. That is what advanced sunrise and delayed sunset. This is possible because of the atmospheric refraction. These are the some of the examples of the natural phenomena that occur in the atmosphere, that occur in our surroundings. So here you can see the various examples, right from rainbow, scattering of light, why sky appears blue and why sun appears red during the sunrise and sunset, and what is Tyndall effect, and atmospheric refraction gives rise to what. Especially the best example is twinkling of star. So the questions can be asked like this: What is the reason for twinkling of star means? You can just write atmospheric refraction is the reason for twinkling of stars. And why the objects are seen shivering or wavery when you are observing through the flame means because of atmospheric refraction. Because as you are looking at an object through the different refractive indices atmosphere, that means atmosphere having different refractive index, then definitely it will not have the unique identity. It will be somewhat differing in its nature, which appears to be wavering. So these are some of the examples of natural phenomena of light.